So in section 6.7, we dedicate this whole entire section to finance formulas, specifically the compound interest and continuous interest formulas. So these are applications of exponential functions is what we're focusing on. So what we're going to have is two formulas. You do need to know these formulas. We have a compound interest formula and a continuous interest formula. They're at the top of the handout. I want to make sure you have some idea what compound interest actually means. So compound interest is where your money earns interest on the interest. So as an example, if you have an account that's compounded monthly, at the end of the first month, they take a look at how much money you've got in the account. They assess the interest, which is a rate, a percentage, and then they add that back into your account and reinvest a little bit more than what you originally had. So, and then at the end of the next month, they take that new amount, they assess the interest on it, add a little bit back in and reinvest that larger amount. So each time it's compounded, you're investing more money, not a lot because it's an interest rate, but you are investing more money. And so compound interest is really great for you. You're earning interest on the interest. So it's great. Your credit cards, your loans, home loans, student loans, car loans, all work off of an idea of a compound interest too. So in general, we'll use something called the compound interest formula. It says A is equal to P times 1 plus R over N raised to the NT power, which is why it's in this chapter because of the exponent sitting up there. A is the money at the beginning. A is the amount of money at the end of time. So at a specific point in time, 5 years, 12 years, 20 years. That's when time occurs. That's A. P is the amount of money at the beginning of time. So how much is the initial investment into that account? R is the interest rate. It must be as a decimal. Never, ever, ever put a percentage into a calculation. Always change it into a decimal first. T is the time. It has to be in years. And N is the number of compounding periods, or the amount of time it is compounded within 1 year. So the different words we'll use with that compounding are annually, where N is equal to 1. Semi-annually would be N equal to 2. Quarterly is N equal to 4. You can do monthly, 12 months in a year, so N equals 12. Weekly, there are 52 weeks in a year, so weekly means N equals 52. We also use daily when N equals 365. Now, our book uses 365. Other textbooks use different numbers. Sometimes over in the business world, they'll use 360 for the number of days in a year. So you do need to be specific upon the textbook you're using. Then what happens is if you actually are compounding it more often than daily, you switch over to what we call continuous interest. Continuous interest is A equals PE to the RT. It spells out PERT, so it's an easy one to remember. So again, P is the principal. A is the amount at the end of time, R is the interest rate, and T is the time still in years. Just happens that if you compound it more often than daily, you switch to continuous interest. So the best way to do these is just jump right in. I strongly recommend as you do these, identifying the variables each time till you get used to doing them, rewriting that formula so you can get used to writing the formula. All those wonderful problem solving techniques come back into play here. So let's jump in. Hopefully you have your calculator out so you can work through the calculations on your calculator also. I'm going to work through writing them up and everything, but leaving you to the actual calculator part. Example 1 starts off and tells us, find the amount that results after 600 is invested at 5% compounded daily after 3 years. So I see the word compounded daily. So that daily tells me 2 important things. It first tells me that this is the formula we're going to use. A equals P times the quantity 1 plus R over N raised to the NT power. So that daily compounding tells me to use this formula. It also tells me that N is equal to 365, number of days in a year. So we also need to find P. That's the amount we're investing. Well, it tells me we're putting $600 in the account. So P is 600. A is what we're trying to find. It says find the amount that results after. So that's the amount at the end of time. That's our unknown. Our interest rate is 5%. So as a decimal, that would be 0.05. And this is for a period of 3 years. So T is equal to 3. So I've identified all the variables in our out formula, and we'll plug them in. So in place of the P, we're going to write 600. We're going to do 1 plus, in place of the R is our 0.05. We're going to divide that by N, which is 365. And then we're going to raise that to the 365 times 3 as an exponent. Now, if you have a graphing calculator, you can plug it in just like it lands and you'll have no problem. Make sure that both the 365 and the 3 are up there as the exponent. If you have a scientific calculator, you'll need to actually start on the inside of this. You'll take the 0.05 and divide it by 365. Once you have that, you'll add the 1. Once you have that, you're going to raise it to this power. You might want to make sure you put that in parentheses. Then when you're done, you'll multiply by the 600 output. So we're following our order of operations. It says do anything inside parentheses, then do your exponents, then do your multiplication. And once you've done that, you should end up with a numerical answer of $697.09. Now it is money, so make sure you round to 2 decimal places. $697.09. So after 3 years, if you put $600 into account, you will have gained an extra $97 using this compound interest. The problem is that the interest rates that our textbook uses are pretty unrealistic. You don't find a 5% interest rate on investment. You really don't. It would be nice, but you don't. But it should show you that yes, the money does grow, which is what we're after here. So that's our first example. Again, hopefully you're walking these calculations through as we're doing these examples. Otherwise, you may struggle with just the calculator usage on these problems. Example 2 asks us to find the principal needed now to get $1,000 after 1 year at 12% compounded continuously. So because we see that word continuously, that tells me to use the PERT formula, A equals PE to the RT. So we need an A, we need a P, we need an R, we need a T to be able to use this formula. Well, find the principal needed now. So the principal is the unknown, and we need $1,000. So let's say you know that you have to repay somebody $1,000, or you need $1,000 to buy something in 1 year. How much do you have to put into the account now so that you'll have the $1,000 in 1 year? So the time is 1 year. The interest rate is 12%, which would be 0.12. Again, too large to be realistic, but it works for the illustration of the problems. So we're just going to plug into this. We're going to have 1,000. That's the amount at the end. That's equal to PE to 0.012 times 1. And we're solving this for P. Well, e to the 0.12 times 1 is e to the 0.12, and we're just going to divide that out. And then go to my calculator. So don't round until the very end. So in general, do some algebra to get the correct answers. If you round and start writing down decimals, you're going to get rounding errors and get the wrong answer. So P comes out to be 1,000 divided by e raised to the 0.12 power. And when you do that, you should end up with your beginning principal is $886.92. And that's where you end up. So if we invest $886.92 today, in 1 year, we'll have $1,000 if we can find a 12% interest rate. And then finally, example 3 has us compare a couple of interest rates. So it wants to know which one is better for us. Oops, sorry. This is part 1. I should label that. Okay, it says, which of the following 2 rates will yield the larger amount in 1 year? 9% compounded quarterly. So 9% quarterly, or 9.25% annually. So what the question's really directed at is which is better for you. Are you better at a lower interest rate but a higher compounding period, or are you better off at a slightly higher interest rate with a lower compounding period? And so that's what it's asking us. In both cases, the quarterly and the annually, you're telling me to use A equals P times 1 plus R over N to the N T power. But they didn't give us any dollar amounts. So we can use any dollar amount we want as our initial investment. So let's let P equal $100, and you can use any number you want. You can use 1,000, you can use 1. I'm going to use $100 because that's what I use when I keep this up. So we'll use $100. For the quarterly, we know that N is equal to 4 and our interest rate is equal to 0.09. And we're doing 1 year, so T is going to be 1 year for everything. So that's going to be a constant. So we're basically just doing the same calculation twice to see which one gives us more money at the end of the investment. So for the quarterly, we'll do A equals our $100 times 1 plus our interest rate was 0.09. We're going to divide that by 4 and raise it to the 4 times 1 as an exponent. Again, on a scientific, start on the inside, use the exponent next and the 100. If you're on the graphing calculator, just never crunch it straight through. And what you should end up with $109.21. So after 1 year at 9%, you gain $9.21. Okay, well, what if we do 9.25%? So 9.25% would be 9.25 as a percent. So as an interest rate, that would be 0.0925 in decimal form. Annually tells me n is equal to 1. Same formula, we're just changing two of the variables. So A is still $100 we want to invest. We have 1 plus the 0.0925 divided by 1 to the 1 times 1 as an exponent, because it's just raising 1 year annually. So when you number crunch that one through, again, some of those ones are meaningless. This one is not. Make sure you catch that one. You end up with 109.25. So we end up with $109.25. So it looks like for us that, oh, I called this one wrong. I can't read my own writing sometimes. Sorry. This is 109.31. That's 109.25. So this one actually is the better one. So in this case, because of the two interest rates, the lower interest rate compounded more often is a better deal for us than that higher interest rate with less compounding. But again, notice it's just 6 cents difference, right? But that's because we only invested $100. If we'd invested $1,000, that decimal would get moved over one more spot, right? And then we can start to see some differences. So now there's, a $10, $11 difference. And if you invested $1,000 or $10,000, the decimal would move again. So you can see some differences with larger investments. And that ends part 1 for us.